Hello, this is the first of 3 videos on number theory for week 5 for Math 407. We're going to be looking at some divisibility theorems. First of all, I would like to look at a simple form of theorem 4. So let's see what theorem 4 is. Theorem 4 is our linear combination theorem. It says that if C divides A and C also divides B, then C divides any linear combination of A and B. A simple form of this is as follows. If D, A, and B are integers, and I'm happen to use capital letters because I felt like it here, just maybe for emphasis, D is dividing A and D is dividing B, then D divides A plus B and D divides A minus B. These are simple linear combinations of A and B, and they might be sufficient for our purposes. Here are 2 theorems. These happen to be exercises in our previous homework, but now we're going to prove them. If m is an integer, then m and m plus 1 have a greatest common divisor of 1. For example, 17 and 18, or 20 and 21. If m is an integer, the greatest common divisor of m and m plus 2 is either 1 or 2. Okay, let's go ahead and look at our handout. And let's prove the second one. And I think I'm actually going to prove this 2 ways. So what we want to do is find the greatest common divisor of m and m plus 2. So we're going to let D be the greatest common divisor of m and m plus 2, and we want to find out what D is. Well, by definition, D has to divide m, and D has to divide m plus 2. That's the definition of greatest common divisor. So, according to our linear combination theorem, D must also divide m plus 2 minus m. And I will say, for emphasis, that this is a linear combination. Well, m plus 2 minus m is 2. D divides 2. Well, D has to be a positive number. To be a greatest common divisor, it must be a positive number. There are only 2 divisors of 2. D equals 1 or 2. But D was what we were looking for. So therefore, the greatest common divisor of m and m plus 2 is equal to 1 or 2. And we saw that we can think of examples for each. Now, I would like to prove this another way, using the contamination theorem. If you need to look back at the contamination theorem, I encourage you to do that. So we're looking for the greatest common divisor of m and m plus 2. I'm going to leave the first component the same, and I'm going to contaminate the second component by subtracting the first component. If this has a similar feel to the last proof, then you're noticing some things. If I simplify, I get 2 in the second position? Well, if D is equal to the greatest common divisor of M and 2, then D divides 2. It also divides M. So we are going to proceed as we did before. There are only 2 divisors of 1 and 2, so D has to be 1 or 2. And then we can substitute to make our final conclusion. Either proof is correct, and only one proof is required, but I think it's useful to consider both. Now I'd like to look at these 2 theorems. If D is a divisor of A times B, and D and A are relatively prime, means they have no common factors, then D has to divide B. So the idea here is that D divides a product, but D does not have anything in common with A. So D must have all its commonality with B. You're going to be proving this one on the homework. The second theorem says that if A divides N and B divides N, and A and B are relatively prime, they don't have any factors in common other than 1, then A times B divides N. And we are going to need this second theorem in order to prove the divisibility test for 6. So let's prove this. Okay, let's start with the given information that the GCD of A and B is equal to 1. And we're going to use Bezout's theorem. It says that we can write a linear combination of A and B that gives 1. There exists X and Y in the integers such that AX plus BY equals 1. And we'll come back to that in a minute. Now let's take our next piece of given information. A divides N and apply the definition of divisibility. This implies that there exists, I'll use K in the integers, such that AK equals N. Similarly, B divides N implies BL equals N for some L in the integers. So we're going to need to combine all these. And we might think about our last line of the proof is going to be AB divides N. So the line above that is probably going to be AB times some quantity is equal to N. So we need to have N on the right-hand side. So I'm going to take my equation up here. I'm going to go ahead and use an arrow here, and I'm going to multiply through by N. ANX plus BNY is equal to N. I've multiplied through by N. the multiplication property of equality. Now, I need to have a common factor of AB that I can factor out. So what I'm going to do is I'm going to substitute for the two n's. In this first n, I'm going to substitute BL. That makes my first term have an AB in it. In the second expression, I'm going to remove n, and I'm going to substitute AK. So I have AB as a common factor. So I'm going to factor out that common factor. See if I can do the distributive property correctly here. AB times LX plus KY is equal to N. So I have AB times something equals N. That something, that quantity, is an integer because of the closure property. And now I can conclude that AB divides N. Again, we've used our definition of divisibility in both directions. This ends our first video, and we're going to be using some of these ideas as we proceed actually into some easier proofs. Our next video is on parity.